Do you find this whole thing about exponentials and half-lives confusing? Plotting a straight line with logarithmic axes? Well, don't worry, you're not alone. So what I've done is I've put together this Excel sheet which will explain things to you rather nicely, I hope. So let me show you what I've done here. And move it out of the way. So if I just focus in the zoom here, what I've done is I've created a column starting representing the time here, 1, 2, 3, 4. So this could be minutes, realistically, it could be any units really, but minutes makes sense, 1 minute. And I started off with a starting off concentration of this totally random number of 1567. I literally just typed it at random. And as you go down, each number here is actually a formula. So it's the previous number, in case this one, times by this value here, 0.8. So in other words, what happens here is that every 1 minute, 20%, because that's 0.8, 20% gets got rid of. So it goes down by 20% each and every time. And then what I've done is I've then plotted that in this graph down here. Right? So if I now, so what we've got here is the concentration, so it starts at 1567 and goes down by 20% every time. And this is an exponential curve. You can work, there is obviously a formula for this, but you don't need it for what I'm going to show you now. So the first thing you could do here is to figure out where the t-half is by picking any point, and you can do it roughly, approximately. So let's take 1600 here. T-half is the time it takes for that to go down by a half. So I know it's not exactly 1600, but this is just estimating it. So let's say 1600, half of 1600 is 800. So where does it get down to 800? Well, it's actually here at 0.4, which is here. So the t-half then now is actually 1, 2, approximately 3 minutes. So this is a classical exponential curve. And the thing is, how would you do this a bit more rigorously? And what you could do is you could measure the gradient at each point, but of course that changes over time. And usually what you do is you want to plot this as a logarithmic concentration. So if you click on any of these numbers, so I was just checking there why it wasn't doing it. You need to double click the number, double click this 1000, and you get your axes here. If you change this down here to logarithmic, well, you get a lovely straight line. What you can do with this graph now that you've plotted it exponential, you've plotted the log, is you can extrapolate this back with a straight line to get to the concentration at t0. If I go back to the original plot, you can't really do that because it's quite difficult to extrapolate this backwards with any reasonable accuracy because it's constantly changing. If I take the log scale, now I've got a straight line, and with a ruler even, I can then just extrapolate back. And this gives me my concentration at time 0, which we don't really know here. And from that, we can work out all sorts of things, such as the volume of distribution and so on. Let's see what happens if you can play around with this plot and see what happens when you change the rate, for example, of decay. So here we're reducing it to 80% each time. So we're getting rid of 20% of the drug. If we only got rid of 5%, 10% of the drug by changing that to 0.9, look what it does to the curve. Right, so it goes down less quickly. Let's do the same thing now with using logarithmic plots. Now if I change this here to 0.8 again, you can play around with this on your own. What does it do? It simply moves it down. Right, so this is all very useful to play around with this. So remember, double click that and change it between logarithmic and linear scale.